Hi, everybody. My name's Arya, and this is our presentation for our final HLS project. My partners are Harsh and Henry, and we're going to be introducing a project on Lighthouse localization algorithm and accelerating it.
Okay, so basically the whole point of this project is that the localization with LiDAR is very compute intensive, especially when it comes to FPGAs and microcontrollers. So here in our whole project is that we're going to have LiDAR, which will be detected using a drone, for example, like this one right here. It will receive a LiDAR signal. And with this signal, we are able to decode its exact location in a free roaming space. And we're going to be doing this, next slide if you wouldn't mind, by basically taking in its input, which will have two signals per sensor, which will be a data signal and an envelope signal. The envelope signal will just tell you the timing, while the data signal will give you the zeros and ones, which are you able to decode to get the exact measurements of where the positioning of this drone is. So next slide, please. So basically, the DOT here will input the data signal and the envelope signal. And since you can have up to like four base stations, this signal can hold four signals of data and four signals of envelope. But while the output itself, since this is going to be outputted to another, this is going to be the computation for the vectors that are computing are going to be UART, which is 96 bits. However, since the FIFO is only 32 bits, we have to package it so that the FIFO only sends one word at a time. And we track that using one of the variables, which is a flag. And we basically wait till three words are outputted from the FIFO to get the 96 bits from the UART, which is expected so we can decode and use matrices, multiplications SVD to get the exact location of the drone. However, for us right now, what we're doing is just decoding the signal so that we can send this UART signal to the CPU so we can do the hard matrix multiplications that we're not able to do. Next slide. So right here is basically how we're decoding the envelopes and data signals. So it all depends on the size of the length of the signal, where 87 nanoseconds and 147 nanoseconds is what determines as a long and short signal pulse. And this is basically just looking at the falling edges and rising edges. When there's two low signal pulses, that's a one. And when there's two long signal pulses, that's a zero. Anything in between that's very ambiguous. And this basically decodes it, giving us the ones and zeros, which we will use later in the shift buffer register, which will take 17 decoded signals of ones and zeros, which we're able to use the code to figure out the polynomial structure as well as the offset. Next slide.
Yes, so now we come to one of the major parts of the project, the polynomial identification and the offset. So this is where actually our project is the most compute intensive. And the first part of this is the polynomial. So once you get the signal, you have 32 possible candidates which contribute to the signal's signature. And you need to find out which polynomial is that. So it's basically brute force, and the code is pretty simple, which you can see here. But the idea is that there are 32 of them. And then for the offset, there are 17 bits. So there's 2 raised to the power 17 possibilities. And these need to be done for every single signal. So that becomes way too intensive in terms of compute and has to be done sequentially. And also in an embedded systems environment, you will have to be doing this for like thousands of signals and in a very short amount of time. So that's the main bottleneck of a project, and that's the part which you're trying to optimize the most. So the polynomial identification basically uses the LFSR approach, and this is the code here. So basically, we go through all 32 polynomials and we see which one matches up with the signal. The next part of this is the offset search, which is also again like brute force, and you go through all the possibilities. But this part is again, it's a much larger number. Like 32-bit, it's still a trivial number, but like 2 raised to the power 17 becomes quite a bit. And then that's where optimization comes into play. So uh, again, the code looks pretty simple and it's brute force again, but we have to do a lot of optimization in terms of splitting up the tasks and actually exploiting the parallelism so that we can speed this up as much as possible. So something that we employ in both the polynomial search and the offset search are lookup tables. A small example of it is visible on the top right corner. So this is for the polynomials, and we have a much larger lookup table for the offset search. So this reduced our latency significantly because um, when you're trying to find the starting point of the LFSR approach, it is very compute intensive because you have to do that every single time for every signal. And instead of going through the entire process of calculating it, the lookup table reduces that period significantly. So once we had that lookup table helped us reduce the latency quite significantly. And then we resorted to our HLS pragmas to further take it down a notch. So over here, I have the example of the offset finder step and a poly finder step. They are very similar pieces of code, but I've put them here for your reference. So we use HLS array partitions, we use HLS unrolls, and those help us kind of simplify the loops that we have here. So obviously, this is much more intensive, the offset finder, and offset finder was by far the largest contributor of latency to our project. And all the others were actually smaller aspects. And I've only highlighted finding offset and finding polynomial here. All the other functions also have some elements of HLS pragmas optimizing them, but they are so trivial compared to these that we're only focusing on these for now. So you can see the array partitions here, and the LFSR states tho- those are stored in this array, and the partitioning allows us to access them in one go. And one of the major implementations that really helped us do this was that we had to split up the LFSR approach into 4 different segments. Now, again, if I would highlight the number, 2 raised to the power 17 was quite a few possibilities. So we decided to do them in one go. And we segmented that into 4 different sections, which would progress in parallel. So the LFSR approach will start at 4 different places and then keep going from there. So the HLS array partitioning and the unrolling lets us do this in parallel and really helps us reduce the latency.
So now we can talk about how prior to even trying to optimize our code with pragmas, we needed to make sure that the algorithm was implemented correctly. And so we did a couple of different types of testing. Firstly, we took each individual function that makes up the pipeline and unit tested them on their own. So there are stages such as the BMC decoder, finding the correct polynomial and finding the correct offset. We tested them on their own for an input that we had where we knew what the offset or polynomial was. And as you can see here, it passed all those tests. Next, we tried to send inputs through the entire pipeline. First, testing just the DUT function to make sure that the correct streams are sent into the FPGA, into our HLS implementation. And then we tested the entire pipeline, which would involve sending in batches of inputs and then running it through all the parts of the implementation that Harsh and Henry have talked about. And then finally collecting the output and then checking whether they make sense. And there's a few more screenshots here that show the results of those tests, and clearly they all passed. And so then we were able to move on to actually optimizing each of these parts of the pipeline. You can move on to the next slide. Yeah. We then, after we optimized it, we then generated the synthesis and then made a Brit stream that we could run on the FPGA. And here's a short clip showing that. It's a bit laggy, but it did end up passing, and we were able to see a good reduction in the number of cycles needed to process the entire input. So it was a bit hard to see there, but here you can we made a table to show the improvements of our optimization. I think the most striking thing that you might notice is that in terms of the Verilog synthesis, the baseline has somewhere in the range of, I think, over a million, like 1.18 million cycles of latency. And then through our optimization and our really aggressive pipelining and array partitioning, we got that down to under 100, which is orders of magnitude faster. And obviously, this comes at a cost. As you can see, our lookup table and flip-flop usage increased a few by a multi-factor of around 3, but this is still a small price to pay in terms of the latency drop you got, especially for something that needs to be working in real time. Below, we've used the metric of initiation cycles, and essentially this just measures the amount of cycles that it takes for a batch of data that is collected per sensor, like every time the sensor has a reading, and to run it through our entire pipeline, which includes the really expensive stages of figuring out the polynomial and the offset. And so the total amount of cycles needed, which was like the most compute intensive part of the entire process, was about halved, which is also quite a strong result.
As you can see by this evaluation, the initiation cycles, which is one of the minor things about the decoding process, didn't seem to be like the biggest impact. However, throughout the whole process, the data processing remains constant throughout, no matter how many optimizations we made, which is surprising due to the fact that you believe from the 1 million latency to 98, there would be some improvements in the data processing. However, that would always remain consistent due to the fact that the data processing is just simply looking at the ones and zeros. However, the initiation cycles, which is just looking through the whole polynomial finder as well as looking throughout the whole offset, is the thing that takes up the most task. And with so many signals coming in so quickly, being able to process those signals really quickly, which is the initiation, is what's most important about it rather than the data processing itself.
And yeah, okay, thanks, Henry. Thanks, Arya. This was our entire presentation about our project. And I hope you're able to highlight the fact that how this system is really important in embedded systems and why real systems need to process sensor data at a really fast pace, where the gap can be as small as like 7 nanoseconds. And our streamlined and more efficient FPGA approach can really help speed that process up. Thank you.